Okay, welcome back. This is week 12, and we are going through problems in preparation for exam 3. We're taking a look at this, another problem from Miriam and Craig. I think I said the last one was going to be the last one, so I guess this is the other last one. So we get a bar, I'll give it a mass of 3 kilograms, and we want to determine the position of X of this little guy right here, that little weight, the slider. I called him MS for my slider, 1.2 kilograms. And such that the period is 1 second, right? So we want period equal to 1 second. Therefore, the frequency of this, the natural frequency of it, is also 1 hertz. So the omega n is going to be 2 pi radians per second. We could get the number, but it's, let's leave it that way. So we have other dimensions listed onto here in a spring stiffness right there. So let's take the stiffness equal to 250 newtons per meter. And you can see that this is not a forced problem right here. Okay, so let's take FBD and IBD. Did I do? Yes, I did. So some side calculation that I did. I went the I went about the center of the thing. I could have. I was actually right here where they because it's 0.4, 0.8. I could do it about 8, about O. It might save me a little tiny bit. Yeah, I'm kind of just going back and forth of whether I would want to do that. I'll just go ahead and do it the way I've done it here. So anyway, this is 1/12 m L squared, right? So we take this and go 1/12 3 times 0.8 squared, or 0.16 kilogram meter squared. So let's start out with that. Let me make this thing at an arbitrary angle there. So we'll try to repeat the same mini sketch. Make them equal to each other. Start putting forces on them. We have a couple of weights right here. I could call this the weight of the bar and the weight of the slider. Don't know if I like that. Weight of the slider because it's going to, anyway. We can ignore these because of, for the same reason that we can have the static. We could do the static deflection of this. And the static deflection, if this is in the equilibrium position, which is about what they're showing right here, that means that the weight already stretched the spring a little bit, so it's kind of like already built into the thing, and they would cancel each other out. We've demonstrated that before. We'll have the force of the spring. Oh, it's going to be pushing down, sorry. Because this thing is moving, we're assuming this thing is moving in the counterclockwise direction. We'll put in some of the supports right here just to give acknowledgement to the fact that they are present in a free body diagram. To leave them out would be a bad thing. All right, so I think I got everybody else out of here. The only thing I want to note is that maybe the force of the spring, I could have written onto there. The force of the spring is going to be equal to 0.4 times K times theta, right? Because the thing is at an angle here at theta in the position shown. Now these other guys over here on the right-hand side, we have to be a little careful. We have a rotation. We know that. We're going to have I, and we can make it look like it's about the center. A lot of times I'll use an alpha right now and then use a theta double dot later. It doesn't really matter. We also have the motion, let's see, the motion of the center of this bar. M, A, did I give the name? I went bar. MB, AB, right there. And then also this rotation that I've drawn on there. And then lastly, we have M slider times acceleration of the slider. Now, we could do a little bit of the kinematics over to the side. So the kinematics. We already did a little bit. No, I guess we didn't really. So we can know that the A of the slider is going to be equal to X times alpha. And the A of the bar is going to be L over 2 times alpha, which we already know is going to be 0.4 times alpha. And I'll change the alpha, I'll change the to theta double dot here in a second. So we take our all-important sum of the moments about O equals the sum of the effective moments. And over here on the right-hand side, we have the force is causing a clockwise direction. We have 0.4 times K. And I went ahead and put in my value of K. So I don't always do that. I didn't wait. So I kind of kept it as symbols. But that's only, that's okay. I have to have a theta right there. But that's a force, and I need it to be a moment. So that's why that gets squared, right? So I have that moment arm that's coming down in right there. And there's nothing else on the left-hand side. On the right-hand side, everything's going counterclockwise, so it's all positive. I have this I alpha right there, so I'll put that in 0.1600, and that's going to be a theta double dot. I've decided to just jump to it because we're doing everything in thetas. And then I do the mass, so it's also positive, MB, which we said was 3, and then times AB, which we said was 0.4, and that's going to now be theta dot, but we have to remember to make it into a moment. So right now it's just a force. When you go to mass times acceleration, it's just a force, so you need to also have the length to make the effective moment. And then lastly, we're going to have plus the mass of the slider, 1.2 times x, but we don't know x yet, and then times theta double dot, but we need a square times the x. All right, did I get that on there? Sure enough. All right, so we can collect stuff on the left-hand side. I did it all at once, so I can pre-apologize and say that we had theta double dot plus, and then I made a big parentheses onto here, and I went 0.4 squared 250 divided by the computer. The other computer wants this at another time. Don't tell me. Ugh, I can't stand computers. What about this guy right here? Are we going to be able to get anything back into him soon? Let's double check on this. I just don't want my computer to stall out. Pain in the ass. Let's go back up there. Okay. Continuing on, let's see, we got these 0.1600, right, and plus 3 times 0.4 squared, and then lastly plus 1.2 x squared times theta equals 0. And we know that all of this right here is omega n. Therefore, and we were able to find the natural frequency. Do we find the natural frequency? Yes, we know that it equals 2 pi. So if we want that to equal 2 pi, we say 2 pi squared is equal to 0.4 squared 250 divided by, I don't know why I didn't, I guess I just decided not to. Plus 3 times 0.4 squared plus 1.2 x squared. Anyway, I'm able to find that x has to equal to 0.5577 meters, which I didn't have The solution, no, there it is right there. Sorry, yeah, I did have the solution. It was in the back of the book. And we got it to match. Yay! Still a 10-minute problem, but demonstrating that you have the ability to adapt to a different type of problem. This is different than you've seen before. Only slightly different, but now you've seen it. So maybe some other kind of variation of this. But honestly, you should be trying these problems out. I might do them in the review class, but I won't do all of them. Some of them are up to you. This would have been a good one to do without watching this video. You should not have watched this video if you hadn't already tried it yourself, or if I did in class. I might do this one in class though. But anyway, enough of me yelling at you. I didn't really yell. I yell at my daughter, but not any other people.